Hi, this is chapter 16 on electrophilic aromatic substitution. So, we mentioned briefly in the last chapter that benzene and other aromatic compounds do not have the same type of reactivity as normal alkenes do. The double bonds that we see within the benzene ring are obviously much different from regular double bonds. So, the reaction they undergo is electrophilic aromatic substitution, where we have some sort of electrophile, something that can accept electrons that are attacking it, and that electrophile will replace one of the hydrogens on the aromatic ring. So it can be halogenated, we can nitrate, sulfonate, hydroxylate, alkylate, or acylate. So alkylation is the placement of just some sort of alkyl group, any number of carbons, and acylation, this is an acyl group where I have a C double bond O with the rest of an R group attached. That's called an acyl group. So very useful series of synthetic transformations that we can do, because this allows us to create a lot of those important aromatic compounds that we talked about in the last chapter, like pharmaceuticals, especially things like that. At least the start of their syntheses usually comes from some sort of electrophilic aromatic substitution, and we're going to talk about all of these, some in more extent than others. So let's start just simply with halogenation, bromination to be specific. We had mentioned that benzene is extra stable. Its pi electrons are less reactive than a normal alkene, whereas a normal alkene would undergo an addition reaction with something like bromine, just like we talked about in the last chapter. If we have Br2 with iron tribromide, right, FeBr3, iron 3 bromide, if we're using IUPAC naming, that's a catalyst for substitution of a bromine onto a benzene ring. So FeBr3, it's a Lewis acid. So that means it has a pretty strong partial positive charge to it. If I have an iron with 3 bromines attached, those 3 bromines inductively pull electron density out of that iron, leaving that iron pretty significantly partial positive. It's a Lewis acid. So if I have something like Br2, what can happen is that some of the electrons on one of those bromines, some of these lone pairs, get attracted towards that partial positive charge. And what we end up with is a transition state where we're halfway forming a new bond between bromine and iron and simultaneously breaking the bromine-bromine bond. So just as the bromine-iron bond becomes stronger, the Br-Br bond becomes weaker. And as a result, that gives this bromine on the end a growing partial positive charge, because it's losing some of its electrons that way that were in that covalent bond. They're headed over towards that bromine there. So the structure of the reactive intermediate can be drawn a couple of ways. It can be drawn like Br with a half form bond to another Br and a half form bond to iron with its own 3 bromines to it. The most electrophilic bromine then is the one on the end, which will then cause the bromine-bromine bond to fully break and to form the product. That's experimentally really what the reactive intermediate most is like. What we can do, though, just to save a little time, because that's a little cumbersome to draw, is to imagine the reactive compound being a Br plus ion paired with this FeBr4 minus ion. So just as if we had totally broken that bond and formed that bond right there. The iron gets a negative formal charge on it when it has 4 bonds to those bromines that way. So nevertheless, the electrophile here is this Br+. That's the reactive substance here. And we need to have a very strong electrophile, something with a very serious positive charge to it, because like we said, the pi electrons in benzene don't just go off attacking anything. They're really very stable on their own, so it has to be a very powerful, very potent electrophile in order for the pi electrons in benzene to attack it. So The way the textbook does it is just has one of those pair of electrons in the benzene ring, so one of those double bonds attacking the Br+. Some possibly more helpful method of drawing that would involve, yeah, let's do that, Br+, FeBr4 with the minus, like our workbook did. Oh, here, let me draw those double bonds in the same direction as it did down below. It doesn't matter what resonance structure you use, but I just wanted to be consistent here to indicate that this carbon on top here is attaching to the bromine as opposed to the one on the bottom. What the workbook does is use that bouncing arrow. So the pi electrons bounce towards that carbon, and the carbon then makes the bond towards bromine. So technically both of these are equivalent, just this one has a little more detail into it concerning which of the carbons is making the bond. So what is very important for us to realize here is that this was benzene originally. It had one hydrogen on each of its carbons originally. So when I make a new bond between carbon and bromine, that carbon is now sp3 hybridized. It has the bromine that was the electrophile, right? There's our electrophile, but now it still has that original hydrogen. So right there is an sp3 carbon. So the aromaticity of the benzene ring had to have been broken in order to rehybridize to sp3. So that's one key important feature, right? The carbon that attacked the electrophile is now sp3 hybridized. Every single time you draw this structure, you must draw that hydrogen that's also attached. So whenever we do electrophilic aromatic substitution, the benzene ring attacks, that carbon has the electrophile as well as its original hydrogen on it, right there. So the other carbon that used to be in the double bond is now positive because it still has one hydrogen attached, but now it only has 3 bonds because it's missing the double bond. What we can do, since we have a 6-membered ring with a double bond next to that positive, I can make resonance structures where I move that double bond over to satisfy the plus charge, but then the plus charge goes to the other side of where that double bond was. Then I can move the next double bond over to satisfy the plus, but then the plus appears up there. So whenever we have a charge on a 6-membered ring like that, that charge gets distributed sort of in a 1-3-5 manner around the ring. So within this intermediate, there's positive charges on those 3 carbons around the ring. It is resonance stabilized, so it's not as terrible as having just a normal carbocation intermediate, but still it's very uphill energetically because we had to break aromaticity in order to get there. So that's why this is very slow. Electrophilic aromatic substitution, at least on things like benzene, do not happen really very quickly, even with that catalyst. So these are typically slow reactions. Because we broke that aromaticity, we need a significant amount of activation energy in order to form that carbocation. So there's a very large uphill barrier in order to form that carbocation. We are not done when I form that carbocation. What we do, right, here's the carbocation. Unless I tell you to draw the resonance structures, you just need to draw this first one, okay, where the plus charge is on the other carbon that once had the double bond. Okay? Then what happens is some base present within the solution, usually it is what came from the catalyst, right? So the FeBr3 catalyst got an extra bromine to become FeBr4 minus, which is basic. That iron minus attacks that special hydrogen that we talked about, the one that's on the sp3 carbon. The electrons between the CH bond then skip down into the ring here and form a new double bond that satisfies that plus charge and reforms the aromatic system. So this step right here, removal of that hydrogen, is very fast. Okay? The slow step, of course, is formation of that carbocation right here. Take a look at this. We start with benzene, huge activation energy, okay, huge barrier to get over. Here we formed that carbocation, okay. Then a very small barrier in order to remove that hydrogen and get down to back to the aromatic system. If that were a normal double bond in the first place, the Br minus or whatever would just attack the carbocation and we would get addition, but that product is still much higher in energy than the aromatic system. Okay? If I did an addition reaction, I no longer have an aromatic ring. In order to get a favorable reaction, we have to reestablish that aromaticity. So that's why instead of bromine attacking the carbocation, what was once the catalyst attacks this hydrogen in order to put the electrons back in the ring. This second step here is very close to what happens in a E1 reaction, if you remember those, where we would form a carbocation and then something would remove a beta hydrogen. Okay? Remember, here's alpha, here's beta. It removes a hydrogen next to that carbocation. Its electrons sort of come down in to form a double bond in there. So it's sort of like an elimination that happens in that second step, but the overall net result of this reaction is substitution, because we started with an H on that carbon, we end with a bromine on that carbon.